Hello everyone. Today we will discuss one of the most important topics in transport phenomena. Flow past a single sphere and evaluation of its transfer coefficient. This topic helps us understand many real life engineering processes, for example, particle separation in industries, heat transfer around the sensors, dissolution of solids in liquids, and many more. So, today we will understand everything step by step in a simple and intuitive way. So, imagine a small ball falling in water or a droplet falling in air. So, these are two equivalent situations. First one is the sphere is fixed and the fluid flows over it. And the second one is the fluid is fixed and the sphere moves through it. So, both produce the same physics. Okay, so now when a sphere moves in a fluid, three main forces act on it. First, the gravitational force, which pulls it downwards. Second, the buoyant force, which pushes it upwards. And third, the drag force, which opposes the motion. So when the sphere starts falling, it accelerates. But after some time, it reaches a constant velocity, and this velocity is called the terminal velocity. So at this stage, the gravitational force will be equal to the buoyant force and the drag force. So this balance comes from Newton's second law, and this is the concept which is the foundation for all the calculations in this topic. So this is the formula which equates the gravitational force with buoyant force and the drag force. In reducing this relation, we get this relation, which is drag coefficient into Reynolds number is equal to 4 by third of Archimedes number. So coming to the discussion of Reynolds number and Archimedes number. Number and Archimedes number are dimensionless numbers. They are used to simplify engineering problems. So Reynolds number is equal to density of the fluid into velocity into diameter of the particle divided by viscosity. So a low Reynolds number gives us a smooth laminar flow, and a high Reynolds number gives us a turbulent flow. Now, this Reynolds number affects the drag force. The second number is the Archimedes number. So, this compares gravity to viscous force, and from the relationship, we can write Archimedes number is equal to cube of the diameter into gravitational force into density of the fluid multiplied by density of the particle minus the density of the fluid, and the whole divided by viscosity square. So this number helps us calculate the terminal velocity. So if the particle is higher, if the density of the particle is higher than the fluid, then the particle sinks, and if the density of the particle is lower than the fluid, the particle rises. Now we will talk about the drag coefficient. So the drag force depends on the Reynolds number, and engineers use experimental correlations to calculate the drag force. Now different Reynolds number gives us different drag coefficients. Drag coefficients are also called as friction factor. So when the Reynolds number is very less than 2, then the friction factor will be equal to 24 divided by the Reynolds number. If the Reynolds number is in between the range of 2 to 500, then the friction factor will be equal to 18.5 divided by Reynolds number the whole raised to 0.6. And if the Reynolds number is very high, in the range of 500 to 2 into 10 raised to 5, then the friction factor is constant and is equal to 0.44. So we have been trying to obtain a single comprehensive equation for the friction factor that covers an entire range of Reynolds number. So finally, an equation was proposed, and this correlation gives us values for friction factor for with any Reynolds number less than 2 into 10 raised to power 5. Now we will learn how to calculate terminal velocity. So by substituting the Archimedes number formula into the friction factor formula that we just learned, we get a final equation. Using this formula, we will find the Reynolds number. So once we get the Reynolds number, we can use this formula to find the terminal velocity. Procedure to calculate the terminal velocity will be first to calculate the Archimedes number using this formula. Second, to substitute the Archimedes number into the Reynolds number formula and determine the Reynolds number. And finally, once we get the Reynolds number, the terminal velocity can be calculated from this equation. So now let's see a numerical which is based on this. Calculate the velocities at which a drop of water 5 mm in diameter would fall in air at 20 degrees Celsius and the same size air bubble would rise through water at 20 degrees Celsius. So these are the physical properties that are given to us. In here, we will first determine the Archimedes number using this formula and the given data. On substituting the values, we get Archimedes number to be 4.46 into 10 raised to 6. Now we'll find the Reynolds number. So we'll substitute the values in our Reynolds number formula, and we get Reynolds number to be 3581. And now using this value, we will find the terminal velocity, which is equal to viscosity into Reynolds number divided by density into diameter of the particle. On substituting the values, we get the terminal velocity to be 10.8 meters per second. Now, for the air bubble rising in water, we again repeat the same procedure. We find the Archimedes number, then we substitute that in our Reynolds number, and finally we get the terminal velocity. So there are many applications of this method in industries. This is used in cyclone separators, dust collectors, sedimentation tanks, fluidized beds. In all these, we use this formula to find the terminal velocity. But have you guys noticed a small difference, a small anomaly in the numerical that we just discussed? So here, the water drop falling in air, the terminal velocity, we determined it to be 10.8 meter per second. But when the air bubble that is rising in water, the terminal velocity was only found to be 0.3 meters per second. So why does this happen? This is because water is much denser than air, so it falls quickly through air. But air is lighter than water, so it rises slowly because water is more viscous than air. So the drag force on the air bubble will be higher. Now we'll discuss how to calculate the particle diameter if the viscosity and terminal velocity is given to us. So in this case, we must rearrange our original formula such that the particle diameter is eliminated. So if we divide both sides by cube of the Reynolds number, this gives us a value. So let's take y, which is independent of the particle diameter and is a dimensionless number, which is defined by 4 by 3 into gravitational force into density of the liquid minus density of the particle minus density of the liquid multiplied by velocity divided by density of the liquid into cube of the terminal velocity. So on substituting, we get the final equation to be this. And by using this value, we can find the diameter of the particle, which is equal to viscosity into Reynolds number divided by density into terminal velocity. So now let's take another example. So a gravity settling chamber is one of the diverse range of equipment used to remove particulate solids from gas streams. In a settling chamber, the entering gas stream encounters a large and abrupt increase in cross-sectional area as shown in the figure below. As a result of the sharp decrease in this gas velocity, the solid particles settle down with gravity. In practice, the gas velocity through the chamber should be kept below 3 meters per second to prevent the re-entrainment of the settled particles. Spherical dust particles have density 2200 kilograms per meter cube and are separated from an air stream at a temperature of 25 degrees Celsius. Determine the diameter of the smallest particle that can be removed in a settling chamber 7 meter long and 2 meter wide and 1 meter high. And the physical properties of air are also given to us. So for minimum particle size that can be removed with 100% efficiency, the time required for this particle to fall a distance h must be equal to the time required to move this particle horizontally a distance l. So time will be equal to h divided by terminal velocity. So we get terminal velocity equals v into h by l. So where v is the average gas velocity. So it is given to us as 3 meters per second. So we substitute these values and we get the terminal velocity to be 0.43 meters per second. Now we'll calculate the value of y using our formula. On substituting the values, we get the value of y to be 4.74. So we get the Reynolds number and the particle diameter. So once we get the Reynolds number, we substitute that in the particle diameter formula and we get the particle diameter to be 92 into 10 raised to minus 6 meters. Now we will calculate viscosity if the diameter of the particle and terminal velocity is given to us. So we divide our original equation by square of the Reynolds number and we get a value x. Now on substituting x into the formula, we get a Reynolds number. So after getting the Reynolds number, we can calculate the value of viscosity using this formula, which is diameter of the particle into terminal velocity into density divided by Reynolds number. Now let's discuss engineering applications. So one application is settling chambers. It is used to remove dust from gas streams. So when gas enters the large chamber, the velocity decreases and the particles settle due to gravity. So we can calculate the minimum particle size that can settle. Next is a falling ball viscometer. So this is used to measure viscosity of liquids. So here we drop a sphere in liquid and measure the time taken and use that to find the terminal velocity and hence we find the viscosity. Third is environmental engineering. So it is used in wastewater treatment. So the particles settle in clarifiers and the design of the treatment plant will be completely dependent on the terminal velocity. Next we will discuss heat transfer around a sphere. So when a hot sphere is in a cold fluid, heat flows from the sphere to the fluid. So without fluid motion, the Nusselt number, which is again another dimensionless number, will be equal to 2. But with convection, heat transfer will increase. Now, when that happens, we have another correlation for Nesslet number, which is known as Rans-Marshall correlation. It tells us that the Nesslet number is equal to 2 plus 0.6 multiplied by root of Reynolds number and cube root of Prandtl number. Now this equation helps us calculate the heat transfer coefficient. There is another correlation which is known as the Whittaker correlation, and it is used for a wider Reynolds number range. So the Whittaker correlation is given like this. Here the range of Reynolds number is between 3.5 to 7.6 into 10 raised to the power 4. The range of Prandtl number is 0.71 to 380. So these calculations are important in many areas like electronics cooling, reactor design, for in design of sensors and probes, etc. Next, we will discuss mass transfer around a sphere. So mass transfer also works similarly. So when a sphere is immersed in an infinite stagnant fluid, the analytical solution for the steady state diffusion is possible, and the result is expressed in the form Sherwood number is equal to 2. Now in this case, the fluid motion, the contribution of convection must also be taken into consideration. So when convection is taken into consideration, we have the Rans-Marshall correlation, which says Sherwood number is equal to 2 plus 0.6 into root of Reynolds number into cube root of Schmidt number. So now this is valid for when the Reynolds number is between 2 to 200 and the Schmidt number is between 0.6 to 2.7. There is one more correlation known as the Frostling correlation, which says that the Sherwood number is equal to 2 plus 0.552 into root of Reynolds number into cube root of Schmidt number. So for this correlation, the range of Reynolds number and Schmidt number are as follows. And finally, we have the Steinberger-Treiber correlation, which says that the Sherwood number is equal to 0.347 into Reynolds number raised to 0.62 into cube root of Schmidt number, and this correlation is valid when the Reynolds number is between 2000 to 16,900. Now let us discuss about real life deviations. So real systems are not perfect, and there are factors that affect terminal velocity, such as when there are a lot of particles together, presence of non-spherical particles, and many more. So in real life situations, particles rarely move in an infinite fluid because the container walls and nearby particles affect the flow pattern and reduce the terminal velocity. Secondly, most particles are not perfectly spherical, and this irregularity in shapes experience a higher drag and cause them to fall or rise more slowly than what we predict using our calculations. Also, when many particles settle together in a suspension, they interfere with each other and create an upward fluid motion. This also decreases the settling velocity. Also, changes in the temperature and pressure and fluid properties during the motion of the particles can also alter the viscosity and density, and hence affecting the accuracy of our calculations. So because of these deviations, engineers apply correction factors and experimental correlations to get realistic results in industrial designs. Now let us summarize what we have learned. So first we learned forces on a sphere when it passes through a fluid. Second, we learned the terminal velocity concept. Third, we learned dimensionless numbers such as Reynolds number and Archimedes number. Fourth, we learned the drag coefficient correlations. And finally, we learned the heat and mass transfer correlations. These ideas are extremely important in chemical engineering design. Thank you.